Hello and welcome to Ask Echometer. My name is Carrie Ann Taylor, and along with myself from Echometer, we have Gustavo Fernandez, who does a wonderful job manning the chat and Q&A session. Also Ken Skinner, Tony Podio, Dieter Becker, and Lynn Rowland, who will be presenting with me today. During these sessions, we want to be interactive with you. We welcome questions and comments from you, and our goal is to answer all of your questions during the session time. There's also an Ask Echometer page that's accessible from our echometer.com homepage, and Lynn has that website address right here on this first title slide here, this echometer.com support Ask Echometer. So you can go there right now if you'd like and download the Session 16 PDF documentation bundle. And so that bundle contains a PDF of today's presentation, as well as several technical papers and videos that we'll reference today. And then right next to that PDF bundle link, you can click the link to download the TAM examples that we'll look at today. If you don't already have the TAM software installed on your computer, you can download it from the software page on the website too. And there's a link from the homepage directly to download the software. Today's session is titled The Three Main Causes of Incomplete Pump Fillage. And so, Lynn, I'll turn it over to you to start us off.
All right, thank you, Carrie Ann. This is a presentation that we'll have. There's about eight examples we'll go through it after the presentation is complete. And if you want to follow along with the examples, then you need to download the TAM software from our webpage and install on your computer. And then the session bundle has the TAM examples in it, and you'll be able to download the data off the webpage. And also there's these technical papers that we've listed are also in the bundle, along with some animations and things like that. So the next slide, we're going to talk about secrets. And when we talk about secrets of rod pumping, you know, sometimes people say, well, didn't you know that was a recommended practice to have your pump filled with liquid? And no, someone will say, no, it's we hadn't heard that before. So the term secret may be a little bit broad here, but what we're trying to say is that there's recommended practices to operate wells, sucklifter wells, and it can be proper chemical treatment for corrosion, preventing rod on tubing wear, doing failure root cause analysis, and then monitoring your well's performance. We can use dynamometers and flow levels to see how your well is operating. Often when a well has a problem and it's not properly addressed, and that problem still exists in the well, and it can be a frequent cause of repeating failure. So if you are not practicing a recommended practice, then you know maybe it's because you just didn't know about it, and it must be a secret. So on the next page, we're going to talk about the top secret, which is operating wells with incomplete pump fillage. Now, why would I say it's the top secret? Because when someone, a customer or an operator, sends us data on a well that they've collected, almost always the pump is not filled with liquid. And so a long time ago, I started saying they just don't know the secret, because we see all these examples of wells that are operated with incomplete pump fillage. And so one of our practices that we had when I worked for a production company, Emerald AS, in the past, it was at all costs maintain a pump filled with liquid, and we believed that would reduce our failure rate, and we saw that we had a low operating cost, and we saw that we had low failure rate. So I'm a large proponent of maintaining a full pump fillage when you operate a sucklifter lift well, but you also still have to have the other recommended practices and follow along those because you just can't do one right and do another one wrong, or you'll still have an operating problem. All right, Carrie, I think you're next.
All right, thank you, Lynn. So starting with a basic pump action review. The valves open when the pressure below the valve is greater than the pressure above the valve. And we're going to take a closer look over the next several minutes at flow through the traveling and standing valves during pump operation. The pressure in the barrel is a function of plunger travel and the compressibility of the fluids inside the barrel. And we have two pressures to define. First, the pump discharge pressure is the pressure at the bottom of the tubing. It's the pressure sitting on top of the traveling valve. And the pump intake pressure is controlled by casing pressure and the fluid column in the annulus. And this is the pressure below the pump at the pump intake. Rod loading from the pump is controlled by the difference in pressure above and below the traveling valve. So let's define this pump plunger assembly. In the center of the illustration is the pump assembly. The green represents the barrel. The red represents the plunger. This is a hold-down assembly fixed to the tubing. Here we have the tubing and the casing, and you see there is a certain amount of fluid in the annulus. The casing pressure and the fluid in the annulus have a direct impact on the pump intake pressure, which is the pressure in the casing at the depth of the pump intake. This pump intake pressure must be greater than the pressure above the intake valve in order for the valve to come off the seat and allow fluid to flow inside the barrel on the upstroke. The intake valve is also called the standing valve. It's fixed to the tubing and considered to be stationary. It acts as a check valve to keep well fluid in the tubing on the downstroke. So during the downstroke, compression occurs inside the barrel, which causes an increase in the pump chamber pressure. So that chamber pressure must be greater than the pressure above the discharge valve or that traveling valve in order for the valve to open and allow fluid to flow out of the pump and then up into the tubing. And so this pressure is called the pump discharge pressure. The traveling valve moves with the plunger, and it acts as a check valve to keep well fluid in the tubing on the upstroke. So we can explain the pump operation in 4 basic cycles here. So if you think of a full pump card with the 4 valve operations occurring clockwise on the 4 points of a rectangle, A being the bottom of the stroke, then at point A, both the traveling and standing valves are closed. As the rods start pulling up, there's a pressure drop inside the barrel. And so from point A to B, there's an expansion taking place inside the barrel. The traveling valve at this point should remain closed to keep fluid in the tubing on the upstroke. Once the pressure in the barrel drops below the pump intake pressure, the standing valve opens. And during the intake cycle from B to the top of the stroke at C, fluids present at the pump intake flow through the standing valve and fill the barrel. At the top of the stroke at C, both the traveling and standing valves are closed, and the fluid in the pump barrel is liquid or a mixture of gas and liquid that exhibits a certain compressibility. So now on the downstroke, the plunger moves down from C to D, compressing the fluid and increasing the pressure in the barrel below the traveling valve. So once that barrel pressure exceeds the pump discharge pressure, the traveling valve opens and the fluid in the barrel is transferred to the tubing as the plunger now moves to the bottom of the stroke from D to A. So before we talk about incomplete pump fillage, let's talk briefly about what we expect to see when we have a full pump. So these 2 illustrated pump cards, or synthetic pump cards, represent normal full pumps. You see the pump operation steps that I just sort of went through from A to D. There's A to B, B to C, C to D, and then back to A here. MPT stands for maximum plunger travel. And the maximum plunger travel is the maximum length of the plunger movement with respect to the pump barrel during one complete stroke. EPT stands for effective plunger travel, and this is the length of the plunger travel when the fluid load is acting on the standing valve, or in other words, the length of the plunger effectively being used to move fluid. So when we talk about fluid load, FO represents the fluid load, or the force applied to the rods due to the differential pressure acting on the pump plunger. Both cards you see here exhibit normal pumping with pumps full of fluid. There's no gas in the pump. The valves aren't leaking. The pump is functioning properly. On the card where the tubing is anchored, the effective plunger travel equals the maximum plunger travel. And on the card with the unanchored tubing, the effective plunger travel is less than the maximum plunger travel due to the tubing movement. So this is a great example of a full pump card in the TAM software. So in TAM, you have the ability to look at several things all at once to help you understand how your pump is behaving. And one really nice feature is that you have the ability to replay the cards being drawn and even to create a movie in the event you would like to capture specific strokes and then maybe send them to someone else to review. So if you click on the events button, this events button up here, you see this event strip showing each stroke that's been captured. So here we have the surface and pump cards being drawn. This is a slider graph displaying the power data that was acquired along with this dynamometer data. And then we have the pump animation. So when you're looking at dynamometer data, you have certain annotations that you can turn on by clicking on the annotations button in the lower right-hand corner of the field view or the details view. And I always like to turn on the pressure displays for the pump discharge pressure, the current pump chamber pressure, and then the pump intake pressure from the fluid level. So on the video, let me get that video running here. On this video, you can watch the chamber pressure drop below 86 psi on the upstroke and the standing valve opens. And then on the downstroke, the compression inside the pump chamber increases the pressure to over this discharge pressure and the traveling valve opens. And we can see here the effective plunger travel matches the maximum plunger travel. The pump is full of liquid. There's no gas in the pump, the valves aren't leaking, and the pump is functioning properly. So now we see this same animation, but with the unanchored tubing. So the unanchored tubing stretch line is turned on here, this unanchored KT. Notice that the unanchored tubing pump is full of liquid, but there is some excessive slippage, and that's exhibited by the pump card leaning over more than that unanchored KT line. You can see here the effective plunger travel is much less than the maximum plunger travel available, but the pump is full of liquid. There's no gas in the pump, the valves aren't leaking, and the pump is functioning properly. So let's step through this next illustrated example. At the bottom of the stroke, both valves are on the seat with an equal pressure of 2,500 psi above and below the traveling valve. The rods start pulling out during the expansion cycle. The pressure in the barrel drops to 180 psi, which is lower than the pump intake pressure, and the standing valve opens. Fluids enter the pump barrel through the standing valve, and at the top of the stroke, both valves are back on the seat. Now on the downstroke, compression is happening inside the pump barrel. And when the pump is full of liquid, it takes very little movement of the plunger, just a small amount of compression to increase the pressure from 180 psi up to over 2,500 psi to push that traveling valve off the seat, now allowing fluid to transfer into the tubing. Now the amount of movement that has to occur in order to increase the chamber pressure to above that discharge pressure depends on the compressibility of the fluid inside the pump. Gases are much more compressible than liquids, so a large change in volume is required to significantly change the pressure inside the pump barrel. So if this example here, you have 10 cubic feet of gas inside a barrel, and the beginning pressure is 15 psi, the plunger would have to move half the distance to the bottom of the barrel just to double that pressure to 30 psi, and then halfway again to double the pressure to 60 psi. Some of you may remember Boyle's law from school, P1 V1 equals P2 V2. And what this law can tell us about gas compression in our pumps is that, assuming a constant temperature, the pressure of a gas tends to increase as the volume of the container decreases. And so this graph is a representation of this. We see this first point here at high volume and low pressure. So as the volume is decreasing, that volume decreases, we see the pressure increasing. Here's an example now where both gas and liquid are entering the pump at the pump intake. So at the bottom of the stroke, both valves are on the seat. We have an equal pressure of 2,500 psi above and below the traveling valve. The rods start pulling up during the expansion cycle. The pressure in the barrel drops to 180 psi, which is lower than the pump intake pressure, and the standing valve opens. Fluids enter the pump barrel through the standing valve, and at the top of the stroke, both valves are on the seat. Now on the downstroke, when we have a pump full of gas and liquid, the plunger has to move farther before the gas and liquid mixture are compressed enough to increase the pressure from 180 psi to over 2500 psi. And now the traveling valve comes off the seat, and the gas and liquid are transferred to the tubing. So how does this look when the card is being drawn? So the rods start pulling up during the expansion cycle. The pressure in the barrel drops to 180 psi, which is lower than the pump intake pressure, and the standing valve opens. Fluid enters the pump barrel through the standing valve, and at the top of the stroke, now both valves are back on the seat. Now it's here that we see the gas interference evident during the compression cycle on the downstroke. That additional movement that has to occur inside the barrel is represented by the shape of the card on the downstroke. And it's this portion of the pump card, along with the pressures and corresponding fluid levels, that we're going to concentrate on today to help us determine what's causing incomplete pump fillage on our example wells. So the next several slides are courtesy of Dr. Tony Podio. So this data was acquired by an instrumented pump that was located at the University of Texas in Austin. And so the researchers there had the ability to change the conditions inside the pump, and everything was instrumented so that they're able to record data while they're changing the conditions in the pump. So here we're looking at the traveling valve on its seat at the top of the stroke, which is 23.7 inches from the bottom. You can see there's a mixture of gas and liquid in this illustration here on the pump. And so we're about to start the compression cycle on the downstroke. So we have some lines on this instrumentation graph, and that's charting the position of the plunger in pink, the pump intake pressure in yellow. This is the chamber pressure in blue, and then the discharge pressure in green. And so this vertical line here indicates where we are in the stroke. So here the upstroke has already occurred. The expansion and intake cycles are complete, and now we're at the top of the stroke. The pressure inside the pump, so this chamber pressure, is equal to the intake pressure. So now the plunger is falling. The chamber pressure is increasing due to the compression occurring on the downstroke. We see the traveling valve is still on its seat, and we're still some distance from reaching the discharge pressure. So still the plunger is falling, and now we're at 11.8 inches from the bottom. We see the chamber pressure is just below the discharge pressure, but now things are happening a little more quickly. So the barrel pressure, that chamber pressure, has reached and now exceeded the discharge pressure. And if you look at the traveling valve, gas is just beginning to bubble around that traveling valve as it's just starting to come off the seat. All right, so now we're at 10.1 inches from the bottom. We see the gas flowing through the traveling valve, and now at 2.8 inches from the bottom, gas and liquid are flowing through the fully open valve. So now here we are back down at the bottom of the stroke, and the traveling valve is back on its seat. So this is the video of the strokes as they were acquired, and you have this video within that PDF bundle for today's session. So again, we're watching the traveling valve here. And we're only going to watch maybe one stroke since it's moving in incredibly slow motion. But looking at the instrumentation graph, we see the strokes represented by the pink waves, right? So here's the upstroke and the downstroke. This blue line, again, is the chamber pressure. And so we see at the beginning of the stroke here, the pressure inside the chamber drops down and is equal to or just below that pump intake pressure that's represented by the yellow line. So now we're approaching the top of the stroke. All right, so you can see here in the video, the unit is now on the downstroke. So during the downstroke, we know there's gas and liquid inside the pump. As the plunger is moving down, the gas is being compressed first. And there's a little pause in the video here, but you can see the gradual increase in the chamber pressure until that compression reaches the liquid, and then it exceeds the discharge pressure. So you can see the differences in the compression on this graph. So if you look here, you see this compression here, and you see a little bit of a change here. So what happened here is the researchers changed the conditions on the unit so that for this next stroke, there's no gas interference. There's no gas at the pump intake or entering the pump, and the pump is full of liquid. So on the downstroke, let's see, let me move this a little bit further here. So when you have a full pump, you can see here on the downstroke, compression occurs quickly. And so that traveling valve comes off the seat almost immediately. And you can see the pressure increase on the graph as well. So at this point, I'm going to stop sharing my screen, and Lynn, I'll turn it over to you.
So we've been talking about the suck rod pump, and there's a publication called the American Petroleum Institute API, and there's a API rod pump designation, and so we've added that feature into TAM to be able to identify the pump. And so when you look at a API suck rod pump designation, it looks like this form right here. And the first two characters are the tubing size. The next three characters are the plunger diameter or plunger size. And then it's either a rod pump run on the sucker rods or the pumps ran in the tube on the tubing, rod or tubing. And then the next one is the type of barrel. And then the next code is the seating location. The next code is whether it's a cup or mechanical hold down. And then there's the barrel length, the plunger length, and the total extension length. And so when you go into TAM and you go to edit and you go to list system and you go to the rod string, then you can drop these drop downs, arrows down on the API pump designation tab when you click this button. And then this pump designation is printed in your report. So when you go to the report, this is at the top of the pump displacement calculations on your sucker rod report. Now, there's a couple of things that are important here on this report. The plunger length. Plunger length is used in the slippage calculation. The plunger diameter is used in the calculation of the FO max and FO from the fluid level. The pump clearances and the plunger diameter are both used in the slippage calculations, and then the pump intake depth. So all of this information is important that you should enter it in when you use your TAM software to calculate the amount of slippage and the reference loads, FO max and FO from the fluid level. Now, when we talk about incomplete pump fillage, and you look at a pump card that is on a well that has incomplete pump fillage, all of the shapes look similar. So when you look here, this is the part of the pump card that's called the compression portion, when both balls are on the seat and the plunger moves down to compress the fluid. And this shape and this shape and this shape look real similar. And so how can you decide what the problem is? Well, there's something unique about each one of these. These are the three different types of incomplete pump fillage. Ones we call fluid pound, which means that there's not enough liquid flowing in from the formation to fill the pump up. So the formation is flowing at a low bottom pressure, and there's just not enough liquid. So we say the well is pumped off, and there's incomplete pump fillage. So this portion of the stroke is incomplete pump fillage. But this portion of the stroke right here is the loads are up at near FO max. That means that the pump intake pressure is low. So to have a fluid pound card, you have to have the pump card load line here near FO max, and you have to have a sudden drop in the load due to a fast change from low pressure to open the traveling valve, and you have to have this missing pump fillage. Now, gas interference is a little bit different because even though you have this incomplete pump fillage here, this loss in the stroke, the shape now is more gradual. This is a more gradual compression because when you have low pressure, if you go half the way to the liquid in the pump, the pressure may only change from 10 psi to 20 psi from here to there. But if you have like 500 or 600 pounds of pressure at the pump intake, to go half the way, the pressure has to change from 500 pounds of pressure to 1,000 pounds of pressure inside the pump chamber. So there's much more change in load when you have a higher pump intake pressure, because as you move the plunger down, there's a bigger change in the pressure, because if you go halfway, you double the pressure. We'll go halfway, the pressure here only doubled like from 10 to 20. From here it doubles from like 500 to 1,000. So it's a much more gradual slope. It's a much more sudden slope when it's a low pump intake pressure, and we call it a fluid pound shape. Now this is called gas interference. For gas interference, the fluid level says that the pump intake pressure is high, so the top of the pump card is far away from the FO max line. So this means the pump card being far away from FO max. FO max line is when the pump intake pressure is 0. And so FO from the fluid level load line is adjusted based on the pump intake pressure, less fluid load. So the pump card is going to be lower, far away from FO max. And so this is an example of a gas interference card. Now, a blocked intake or a choked intake pump card looks a lot like a fluid pound card, because on the inside the tubing, the pump appears to have very little or no inflow. And so when the pump loads on the upstroke are near FO max, and the load line on the downstroke is near FO max, just like a fluid pound card, because the pressure inside the pump chamber is low. And then suddenly, when the plunger gets close to liquid, the load quickly drops off, and often we'll see this little negative load here when the plunger has a impact of the liquid inside the tubing. You don't really see a negative load line here, load drop below the zero load line on a fluid pound card, but often you see it on a blocked intake card. But the thing that confirms it's a blocked intake, there's no fluid, usually fluid production at surface, and the fluid level load line says the pump card should only be this tall. So the pump card is at FO max because there's no fluid entry, no pressure entry from the outside the pump. So the pump intake pressure is 0 on the upstroke because there's no inflow from the outside. But on the outside, the pump intake pressure is high, and the pump card shouldn't be as tall as it is. It should be much shorter. So this is the key: a high fluid level with no fluid entry into the pump, and the pump's not full. So there's fluid above the pump's not full. It looks like a fluid pound card, but there's no fluid to surface. So this is an example of a blocked intake or choked intake. So when we look at the pump card, we're talking about this portion of the stroke from C to D when both balls are on the seat. So at this point on the upstroke, the intake valve is off the seat, same valve is open, and then right here at the top of the stroke at point C, both balls are on seat, and the pump becomes a compressor, and the plunger moves down, and it moves down. This is on the downstroke, and the volume gets smaller, and the pressure goes up until the pressure inside the pump chamber is greater than the discharge pressure above the traveling valve, and the pressure inside the pump chamber opens the traveling valve to discharge fluid in the tubing on the downstroke. Now, when you look at a pump card, now this example right here, we've put on each of the slides where there is a surface card and pump card, the example file name. So we'll go back and look at these examples when we finish the presentation. So this is showing the 3 pump card load reference lines, and we use these load reference lines to help us understand what type of incomplete pump fillage is occurring in the well. So the pump card, when there's no excess mechanical friction, the pump card sits on the 0 load line. So on the downstroke, there's no difference in pressure, very little difference in pressure across the traveling valve. So the pump card sits on 0 load line because there's no load on the rods from the pump. On the upstroke, the pump card should be close to or on the load line calculated from the fluid level. So the load line calculated from the fluid level is the discharge pressure above the trailing valve minus the intake pressure below the trailing valve. That's the differential pressure acting across the pump times the area of the pump, and that gives us this load line calculated from the fluid level. Now, the other reference load line is the FO max line, and the FO max line is the maximum fluid load that acts on the pump can apply to the rods, And so that would be the discharge pressure minus 0 intake pressure, the well's completely pumped off, times area of the pump. And so when the pump card goes up to FO max, that means the pump intake pressure is near 0. So how do you use those load lines to understand the problem? Well, if you're a fluid pound pump card, then the pump card fluid load is up at FO max, which means the pump intake pressure is low, and the fluid level fluid load from the fluid level load line is also up at max, and that means we shot the fluid level and the well's pumped off. So those two conditions must be satisfied to have a fluid pound card. To have a gas interference card, the pump card load line is below FO max, and the fluid level that we shot is below FO max. The fluid load line calculated from the fluid level is below FO max, and usually the fluid load line from the pump card and FO from the fluid level show the same load, and they're below FO max. Both of them below FO max, the maximum load line, if the pump intake pressure is 0. Now the blocked intake, where the flow is choked off going into the pump, is different. When you look at the blocked intake, the pump card's up at the maximum load line, which load line is up at FO max, which means that the pump intake pressure is 0. Well, you shoot a fluid level and the pump intake pressure is not at 0. So how come, when you look at this one, the pump card is up at FO max, while the chamber pressure is 0 on the upstroke, because there's no pressure flow from the outside of the pump to inside the pump chamber, because the intake valve, the standing valve, is choked off or blocked off. Well, it could be that there could be a filter that's blocked off. It could be the gas separator is filled up. It could be the end of the tubing is stuck in sediment, but somehow there's no pressure flow from the outside of the pump into the pump on the upstroke. And so the pump card sees a 0 chamber pressure on the bottom of the traveling valve and the discharge pressure on top. So where does this fluid come from? Well, the fluid comes from slippage. So this pump displacement, this stroke right here, is from slippage between the plunger and the barrel. And they typically will be consistent because every stroke you'll see the same amount of slippage. And so if you were to overlay many strokes with a blocked intake card, they should all match up and be almost identical. All right, and the other thing is the fluid level FO line is going to be much lower than FO max, and it doesn't match up with the pump card. So there's something not quite right here. There's something wrong when you see this right here. Well, it's a blocked intake. So this is a well where there's not enough liquid to fill the pump chamber. It's cause number 1. The well's pumped off. The pump intake pressure is low. We'd say the well is pounding. There's a sudden change in load on the rod. So here is on the downstroke, the plunger didn't slow down very much. The rods didn't slow down because there's very little compression acting on the rods. And so right about here, the plunger suddenly slows down and there's a sudden change in load. And that causes the rods to slap the side of the tubing, downhole. That causes pin breaks, causes increased failures when you have incomplete pump fillage like this. This is a fluid pound card. The pump card load line should go up to FO max. This is anchored tubing and this is unanchored tubing. This is the example where we look at the well. We see that there's incomplete pump fillage, and a small amount of liquids enters the pump chamber, and the fluid level is down at the pump intake, at or near the pump intake depth. So this is a low pump intake pressure. Not enough. The pump displacement appears to be 100 barrels a day, but it's only making 40 barrels a day based on incomplete pump fillage. Now this is an animation screen capture from the analysis plots, and what we're showing here is we're showing the pump motion and the polish rod motion here, and the green is the plunger velocity, and the red is the polish rod velocity. And what I want you to see is that on the upstroke we're carrying the fluid load, and on the downstroke here the plunger velocity is about the same as the polish rod, and then right here it suddenly slows down. The pump slows down. And so what you're seeing here is on the downstroke, notice on the downstroke, the plunger velocity and the polish rod velocity are about the same until right about there, the pump almost stops. And when it almost stops, there's a sudden change in velocity. there's an inertia and momentum, and that causes the rods to slap the tubing and starting to loosen and cause the pins to loosen and have a pin break in the well. So that's often a common problem of fluid pound. A sudden stopping, see, it suddenly stops or almost stops right before the valve opens. So it doesn't really pound fluid, it stops right there before it pounds fluid. All right, so here's just a picture of the same thing, and this is a hard pound pump stops as example data. And this is a picture of the railroad cars, and the railroad they stopped, and so the cars ran off the track, kind of like the rod string does on the inside of the tubing. So when you look right here, this is the load versus time, and that's a green, the pump load, and the red is the plunger velocity versus time. And this piece right here is this piece right here, and this is beginning the downstroke right there on the downstroke, and right about here, right about there, is right about there. And now the pressure inside the pump chamber quickly increases as the fluid load transfers from inside on the tubing onto the sucker rod, off the sucker rods to the tubing right here. A sudden change in velocity, but the load transfer occurs, and the plunger quickly slows down and almost goes to zero velocity. And that's what you see at the surface when the bottle wiggles and the plunger slows. That's what's happening downhole. It's not really pounding into fluid, it's suddenly slowing down and almost stopping. And that's what causes problems downhole. So this is a fluid pound example. Now the nice thing about a fluid pound example well is that you can, if you identify that well, you can typically put that well on some kind of device to control the runtime. You could put a low-cost timer, percentage timer on the well to reduce the runtime and only pump when it's full. That takes time to go out and check and make sure it's set properly. You could put a pump off controller on the well. The pump off controller can monitor and see when the pump's not full. And when it's not full, it turns off, and then after a certain amount of time goes by, it turns on and pumps full. Again, turns off when it's not full. Or you can have a variable speed drive to try to slow it down and run at a constant speed and not have incomplete pump fillage. So those are typically the three things that you can do to maintain a full pump. By controlling runtime and maintaining a full pump, you improve the efficiency because you only pump when the pump's full and you don't waste horsepower compressing the gas. You reduce the shock loads. There's a shock load right there when you open the valve, the trailing valve on the downstroke to release the fluid load, creates a shock load, and you reduce failures. We'll talk about that a little bit in a minute. So this is our fluid pound card. We have the fluid level down at the pump. We have incomplete pump fillage. The pump card loads up at FO max. So this is an example of a well that has fluid pound conditions, and we would want to use a timer, pump off controller, or variable speed drive to eliminate the incomplete pump fillage. This is a gas interference card, a synthetic card, and that's cause number 2, gas interference. In this case, the pump card load is below FO max. That means there's a pump intake pressure greater than 0 on the outside of the pump. And notice that the compression portion of the cycle here is gradually curved. That means the pressure at the pump intake is high, and as the plunger moves down, the pressure quickly goes up. And so that's a gradual change in the fluid load as the compression occurs. When you have gas interference in your wells and you allow gas to partially fill the pump, usually the result is increased rod on tubing wears and a hole in your tubing. So when you have incomplete pump fillage with gas interference, rod on tubing wear is a common problem, and its common problem is to have a hole in your tubing. So this is the example. We have a high gassy fluid level. We have a high pump intake pressure. Pump intake pressure is around 700 psi. The height of the pump card, we can calculate the pump intake pressure. Here's a fluid level pump intake pressure around 700. Here's the pump intake pressure from the pump card calculation. They're about a little below 700 pounds. We have the pump card far away from FO max. The fluid load line calculated from the fluid level is far away from FO max. And we see this gradual compression curve. Incomplete pump fillage. So this is an example of incomplete pump fillage. Now, when you have incomplete pump fillage, you need to run a properly sized gas separator that has a capacity to separate gas that exceeds the maximum pump displacement. So on our web page, you can download a gas separator design program called the Gas Separator Simulator software. And you can enter the dimensions of your separator, and you can calculate the length of the dip tube and the capacity of the separator. And here where the separator is approaching the separator capacity is 96 barrels a day, and the pump capacity here is the pump displacement is 96. And we're getting ready to speed it up one more time. You'll see that when the pump displacement exceeds the separator capacity, that the gas gets pulled into the dip tube and you have incomplete pump fillage. So as long as the gas gets out of the separator on the downstroke, the separator is effective. But if the gas bubbles here don't get out of inside the separator on the downstroke before we start at the upstroke, then that gas is trapped and never gets out, and eventually it gets pulled into the dip tube into the pump chamber. And so on this very next stroke here, our pump displacement is 120, our separator capacity, separate gas 96. We start to pull gas into the dip tube, and now we have incomplete pump fillage. And so that's what this separator simulator shows, and it says you've exceeded the capacity of your separator, and you don't want to do that because that'll increase your failure rate. So your casing size is what limits your gas separator size. The separator that you want to run in the well, you need a large area to have a large separation area between the dip tube and the inner ID of your separator. So the biggest separator OD you could put in would be the size of your casing, but you still need some room for the liquid to flow on the outside of the separator, so you can't make it that big. So in this case, if you have a casing size of 4.5 inches, the maximum gas separator capacity you have is 275 barrels a day. So you can't expect to run a suck rod pump in 4.5 inch casing that has a pump displacement more than 275 barrels a day. You'll have, and if you have gas interference, that will limit your pump displacement. 5.5 inch casing, you have a maximum gas separation capacity of 445 barrels a day. 7-inch casing, you can go from 644 up to 1,000 barrels a day. So when you limit your casing size, you also limit your gas separation capacity, and you limit your maximum pump displacement with the suck rod lift well that you can run in that size of casing. So consider using the separator simulator to design your gas separators. The casing size restricts the maximum gas separator supply size, and that also restricts the maximum pump displacement from your well, because if you have it full of gas, even though you can pump more rate, you can't pump the liquid, so you're really restricted by your maximum gas separator size. And so you should try to design a separator that has a separator gas separation capacity that exceeds your pump displacement, your maximum pump displacement. And a gas separator is what you use to address your problems due to gas separation. So here's a pump that's partially filled with liquid. It shows on the very top of the upstroke at point C, at the very point top where both valves go on seat, and the suck rod pump becomes a compressor, compressing the gas. The plunger moves down, the pressure increases until the pressure inside the pump chamber at point D is greater than the discharge pressure above the trailing valve, and the pressure inside the pump chamber opens. The trailing valve displaces the ball off the seat, and the fluid then is discharged into the tubing as the plunger moves on the downstroke after the trailing valve opens. This is this modified Boyle's equation that Gary talked about earlier. It shows that the pressure and volume at the intake is equal to the pressure and volume divided by the gas compressibility factor at the discharge. So let me see if we can explain this. So this is the stroke length, 90 inches, and this is the gas compression curve on the downstroke from intake pressure here to discharge pressure when the trailing valve opens. The discharge pressure is 2,000 psi. So when this compression curve gets to that point right here, the pressure inside the pump chamber, this is the pressure inside the pump chamber being plotted from different intake pressures. So we start here at this point at the intake pressure. As the plunger moves down, the pressure increases until it goes from 500 psi right there to 2,000 psi right there, and the trailing valve opens on the downstroke, and the trailing valve in this case, if the pump's half full of liquid, then the trailing valve is about 15 inches away from the liquid level if the liquid are all at the bottom of the plunger or inside the pump chamber, 15 inches away from the liquid. So there's 15 inches of liquid and 45 inches of gas. I said it wrong. 45 inches of liquid at the bottom of the downstroke has been displaced in the tubing, and then 15 inches of high pressure gas at 2,000 psi. At the top of the upstroke, right here, we're 9 inches from the bottom of the stroke, we have 45 inches of gas and 45 inches of liquid. So we go from 45 inches of gas at 500 psi to 15 inches of gas at 2,000 psi. Now let's look at the low pressure, which is 10 psi. Here we start at 10 psi, and we move half the distance from 90 to 45 inches. Move half the distance, and how much did the pressure go up? Well, the pressure just doubles. So it goes from 10 to 20 psi. Okay, so right there, pressure inside the pump chamber is about 20. And so the load hardly changed at all. So that's why the fluid pound card load right there looks like it's flat, because there's not much change in the intake chamber pressure, and the discharge pressure is staying fairly constant. And so we're not really seeing any change in load on the downstroke as the plunger moves down to compress the gas. But now we move from here to here about halfway, and it goes from 20 to 40. Halfway it goes to 80, and halfway it goes to 160, and now it goes quickly and quickly increases until when the trailing valve opens, there's only about 2 inches of gas inside the pump chamber when the trailing valve opens, when the pump intake pressure was 10 psi at the intake. So here we go from 45 inches of gas at 10 psi to compress that 45 inches of gas at 10 psi to 2 inches of gas at 2,000 psi. So that's a gas. This is a low pressure gas compression curve. This is a high pump intake pressure gas compression curve. And so all these conditions have gas partially filling the pump. This shape of compression curve is due to low pressure gas. This shape of the compression curve is due to high pressure gas. Now, if you were to draw the fluid load, here's a fluid load on the pump card. If it were 500 psi pump intake pressure, this would be a gas interference shape card. And this is a fluid pound card if the fluid load would be up at FO max. This is a fluid pound card. Both pump cards are filled to half the distance with liquid and half the distance with gas. The only difference is the shape. The difference is the fluid load here is based on 500 pounds of intake pressure, lower fluid load. Here the fluid load is based on 10 pounds of pump intake pressure, same discharge pressure. And the shape of the compression curve is compressing the 500 pounds of gas versus compressing the 10 psi of gas. This is our example well that is called gas interference. And so on the downstroke, we're compressing gas on the downstroke. And what we want to look at is here's a gas compression portion of the stroke. So this right here is that right there. And here, when we start to compress gas, what's the plunger velocity? It starts to slow down. So if you look at this, here is the green is the polished rod velocity, and the red is the plunger velocity. And right about here, when we start to compress the gas, the plunger slows down. And so when the plunger slows down at the bottom of the rod string, you have a train wreck. And the rods start to rub on the tubing and create a hole because the polish rod's coming down fast and the plunger is starting to come in. It slows down. And so here's this animation, and I've got the equivalent gas repump fillage line here shown. And so this, from the blue line to that top of stroke, is the total amount of gas that enters the pump chamber. And that's where the chamber pressure, where the trailing valve opens, is approximately 700 psi to open the trailing valve. And so you can see, if you look close, you can see on the downstroke over here that when you start on the downstroke, it goes fairly fast and quickly slows down to right about there, and then it speeds right back up. And so this is an example of a well that has incomplete pump fillage due to gas interference. So this is just a kind of the idea of the train wreck effect. The gas compression on the downstroke, it occurs when the pump is partially filled with gas and liquid, and the reduction of life of the run life of the equipment is due to the compression of the, not just the compression, it's due to the pump slowing down, causing an issue with either the couplings loosening by whacking the side of the tubing, or the rods rubbing on the tubing, increasing holes in tubing. This pump slowing down is a problem. It has to slow down to compress the gas. It has to apply a pressure to increase the chamber pressure to open the trailing valve. And that tends to cause an increased rod-on tubing wear. Now, this is a slide that shows the peak polish rod load, which is created by us picking up the fluid load. We call it the F1 force, and this is the minimum pump load created by us releasing the fluid load on the downstroke. And there's a rule of thumb that says that the peak load divided by the minimum load shouldn't exceed, there's different rules of thumb. The old one I used to have was it shouldn't be less than 0.25. Well, the actual rule that came out of a data study of 6,000 wells and a paper that we reference on the front of the presentation, and it's in the package that you can download. For every 2,500 foot of depth, the peak polish rod load by the minimum load shouldn't be less than 0.01 per 2,500 foot, so 0.2. So in this well, we have a depth of 4,800 feet. The ratio is 0.25, and if you look at the limit, 0.1 per 25 foot, it's that should be a 0.19, not 1.9, 0.19. So in this well, 0.25 is more than 0.19. Why does this matter? Well, whenever you have incomplete pump fillage, then that release of that fluid load on the rods, you get a decrease in the minimum load, and that's going to cause this an issue with this ratio, and you'll see an increase in your failure rate. So watch out for this ratio of minimum polish rod load divided by peak polish rod load, and use that as a guideline. Try not to have your minimum load divided by your peak polish rod load be less than 0.1 per 2,500 foot of pump depth. So when we say fluid pound or rod buckling, the fluid pound isn't really the correct term, because the plunger is not really pounding into the fluid, because the gas in the pump chamber is being compressed and the plunger is slowing down. It's not the compression, the plunger slowing down, that's a problem. It's not pounding fluid that's a problem. It's the uphole conditions where the rods start to buckle and start to rub on the tubing, trying to compress the gas inside the pump chamber to open the trailing valve. And this occurs when you have low pressure gas, you have free gas in the pump. Even if the plunger is only a 1/16 of an inch away from the liquid, it still slows down to open the trailing valve and doesn't pound into the fluid if there's free gas in the pump. Now, this is an example, case number 3, where we see this negative load right here. And this is an example where you see this acceleration impact load when on the downstroke the plunger is maintaining a fairly constant velocity until there suddenly it has to stop when it hits the liquid and the trailing valve knocks open. So this is a blocked intake. And when we shot this fluid level on this well, the fluid level was high and there weren't any, wasn't any gas flow up the casing. So this was a gas-free fluid level, has a high pump intake pressure. The pump intake pressure is 1400 psi on the outside of the intake. And so this pump card should be FO from the fluid level. The pump card should only go up to 2,590 pounds, but the pump card's up at the maximum load as if the pressure on the intake is 0. Well, the pressure outside the pump intake is 1,400 pounds because we see this high fluid level. But the pressure inside the pump chamber is 0 because there's no fluid flowing into the pump. It's blocked off. So this is an example of a pump card that has a blocked intake. And there's 4 different things that you see. You see typically a fairly high fluid level that's gas-free, usually no flow. The well's at static condition because this well's not pumping. There's no fluid coming out of the surface because the intake is blocked off. If you looked at all the strokes are going to look about the same. You often see this negative load when the plunger hits the liquid, and you'll see the pump card load up at FO max, but you'll see the pump card load far above the calculated load line where it should be based on the fluid level shot. So those are the symptoms of a blocked intake pump card. Now, when you look at the blocked intake pump card, we show that the pump card's up at FO max. We show that the pump card height should be at FO from the fluid level, and it's not. And we often see this negative load when the plunger hits the liquid. And if it's anchored, it's a vertical line. If it's unanchored, it leans over based on a tubing stretch. And so this is an example we just talked about where there's something that's plugging off the intake. It could be paraffin, it could be scale, it could be sand, it could be debris. You could have your intake down in the mud. In some cases, it could be asphaltenes or heavy crude. Heavy crude is more likely to restrict the inflow, not completely block it off. And so you'll see a much higher fluid load, but you still may have some production. So it may just be choked, partially starved, not completely blocked off if it's a heavy crude. So here's change the animation. It's no longer the railroad car is off the track. It's a collision, and the collision is the plunger running into the liquid inside the pump chamber. And what we see here is we look at this, we can see the plunger velocity in red, and the plunger velocity is fairly constant until it suddenly slows down and stops after the trailing valve opens, not before. So it slams into the liquid and opens the trailing valve, and then it stops. Before, when it was gas compression, low pressure gas compression, it would slow down and almost stop before the trailing valve opens. Here it stops after the trailing valve opens. Another condition that is usually seen when you have a blocked intake. So here the pump stops. It's got 0 velocity for about a second. It stopped because of it had no gas to compress, and it suddenly runs into the liquid, and the trailing valve opens, and the pump stops for a while. And you see this negative compression impact load at the bottom of the stroke. And there's just an animation showing, and what I want to show here is the main thing is that you see this constant velocity until it hits the liquid, and then it has that little impact load, and then we see this negative load on the pump card. So the pump card 0 load line, FO from the fluid level and FO max line can be used to identify the incomplete pump fillage, and that's what we've talked about in this presentation so far. And that there's a reference, there's a technical paper that you can read that talks about it. The fluid pound card and the blocked intake card look very similar, except that in a fluid pound, the fluid level is at the pump. In a blocked intake, there's a fluid level above the pump, and the pump should be full, but it's not. So the intake is blocked off or choked. The fluid pound and blocked fluid pound card and gas interference card both have gas inside the pump that must be compressed. During the compression cycle of the pump from point C to D when both valves are on the seat, when the intake is blocked, there's no gas inside the pump barrel, and you tend to see this negative load when the plunger pounds into the fluid inside the pump barrel. And that's I think the plunger's actually hitting the liquid because it's not slowing down. Whereas the compression of the gas, the plunger slows down before the trailing valve opens. So what problems are associated with incomplete pump fillage? And how much incomplete pump fillage can you tolerate? Well, not very much. Only 2%, more than 2% of your runtime, if you have incomplete pump fillage, you start to have problems due to that. You have rod buckling, pump wear, rod and tubing wear, you have vibration stresses, you have severe load changes, and you have pumping at vibrations, and this is caused by excessive strokes with incomplete pump fillage. This is a paper that talks about that. It's a paper that I was a co-author on with Steve Galt from Oxy. Oxy has like 6,000 suck rods that are that they have failure data on, and they looked at all of their failure data in the past, and they found that when the pump transfer, the load transfer occurs at the top of the stroke, then the plunger velocity is low. But if you have incomplete pump fillage and there's incomplete pump fillage, and the load transfer doesn't occur at the top of the stroke, then you have an increased failure rate. And so this is a plot of the 6,000 wells data, and this is the life, mean time between failure. And this is a correlating parameter of the stroke length times the strokes per minute. And so if you look at, let's say, 100-inch stroke length and 10 strokes a minute, that would be that line right there. If you would have a 7-year run life if your pump is not full more than 2% of the time. If you have 150-inch stroke length and a 10 strokes per minute, and your pump is not full more than 2% of the time, then you have a mean time between failures of 1.5 years. So as you pump faster, longer stroke, and the pump's not full, you have a decreasing run life, is what this line shows right here. If your pump is full, then you can have a long run life as long as the pump's full of liquid, and that's what this shows right here. These are much longer run lives. And so this is a relationship between stroke length and pumping speed. And so if you look at this table, if you had a 10-year run life, as this blue line right here, if your pump is full and you're operating 14 strokes a minute, it's okay as long as your stroke length is not more than 54 inches. If your stroke length is 144 inches and your pump is filled with liquid, then it's okay. You have a 10-year run life as long as you're not pumping more than 5.2 strokes a minute. So where does this come? Why is this sort of important? Because sometimes people argue that long and slow is the best way to pump wells, or short and fast is the best way to pump wells, and it doesn't really matter whether you're short stroke and fast or long stroke and slow. It's the combination, and the most important thing is your pump filled with liquid. Okay, that's it. So it's not really the short and fast or long and slow is the way to go. The way to go is to operate with a pump filled with liquid. You need to maintain a high volumetric efficiency. You need to match your pump displacement with inflow. If your pump's not full and you're pumped off, you need to control your run time by a pump off controller, or a percentage timer, or a variable speed drive. If you have gas interference, you need to eliminate the gas interference and design a analogous gas separator with a capacity that exceeds your pump displacement. It's important to have a properly sized gas separator, or you'll have incomplete pump fillage and a higher failure rate. If your pump's not full, you need to use runtime to match your pump displacement to inflow. So the way to go is to produce your wells with the pump filled with liquid. You have less problems, more efficient operations, lower failure rates when the well is full of liquid. Incomplete pump fillage is a big factor in causing problems when you're operating your wells. Be determined to operate your pumps filled with liquid. Also, you still have to do the other things right. You just can't say I'm going to operate a pump, but you have severe corrosion problems. That doesn't fix the problem. You have to address all your problems, but you have to address incomplete pump fillage also. So operating with a full pump, is it a top secret, or is it just hard to do? Well, it's both. It's sometimes it just seems like people are not willing to address incomplete pump fillage, and a lot of the times you see pump cards that are not full. I think that's my end of the presentation.
Well, thank you, Lynn. We have just a few questions today before you jump into some examples. And the first question is, I think, is related to slide number 9. And he's asking if you can please explain what causes to have a slanted dyno car when the tubing is unanchored.
Okay, slide number 9. If you look at the bottom of the screen, there's a value called unanchored tubing KT. And what that means is if you have a force, the force that you apply to a length of pipe, and this length of pipe is a tubing, force is equal to KT times the distance that you stretch the pipe. Okay, so that's what this KT stands for. And so this line right here is the amount of stretch you get from the tubing, and we would see this is about 10 inches of stretch. And so how does that make any sense? Well, you've got 464 pounds per inch of stretch, and the fluid load is about 4,069 pounds. So if you take 4,690 pounds divided by the spring constant, that means that you're going to stretch the tubing 10 inches to pick up the fluid load, and unstretch the tubing 10 inches over here when it's unanchored. If it's anchored, then the tubing is stretched already, and it doesn't stretch due to picking up the fluid load. So when you have unanchored tubing and you're picking up the fluid load, then the plunger moves up and you lose that now your stroke. And the tubing is like a giant spring. So it stretches and unstretches elastically because you haven't exceeded the yield strength of the rod, of the tubing or the rods. And so we have a yield strength KR for the rods, not yield strength, but a tubing stretch for this tubing, 464, and a spring constant rod stretch coefficient, 176 for the rods. And so you see the rod stretch here in the surface card, along with the tubing movement if it's unanchored tubing, along with the slippage. Now there's also slippage right here that the plunger moves with respect to the barrel. So you have, in this example here, this slope right here is the slope of the surface card due to the rods stretching, picking up the fluid load, the tubing stretching, picking up the fluid load, and the plunger moving because of fluid slipping between the plunger and the barrel. Okay, now on this slide, since the tubing is anchored, let me stop this. Since the tubing is anchored, this line's vertical, and you don't lose. It's not vertical, it's almost vertical. This line's vertical because there's no tubing movement, but there is, the plunger moves over a little bit of plunger movements right there due to what? due to slippage between the plunger and the barrel picking up the fluid load. So as the pump intake pressure, the chamber pressure goes from like 3,700 psi down to 86 psi. This pressure starts to shove liquid between the plunger and the barrel, and the plunger moves up a little bit. That's slippage. So there's three things that cause this. The plunger to you see these slopes here. You see the rod stretch in the surface card. This slope, which is called KR. You see unanchored tubing stretch line. If the tubing is anchored, it's vertical. But if it's not, if the clearance is zero, it can't be clearance or zero clearance or it's stick. So I guess that's a long answer, but you see the pump card lean over because of the slope of the line is the slope of the spring constant for the length of the tubing. So that's a long answer. I hope that's a good enough answer.
Daryl is asking if you have an animation or pump card for a well which has paraffin buildup. What shape of pump card will I have to look for?
We talked about that in one of the first Ask Echometer sessions, and it's called mechanical friction. And so when you have paraffin, the paraffin usually occurs near the surface when the surface cools off and causes a paraffin to deposit. So maybe in the top 1,000, 2,000 feet, once the paraffin can appear at the appearance temperature, then you start to get a coating of paraffin, and the paraffin starts to apply mechanical friction to the rods. So the pump card is concave outward above the FO max line if the pump intake pressure is zero, and the pump is concave outward below zero on the downstroke. So that's the pump card. It's kind of like it can look like a balloon kind of almost on the top and the bottom of the pump card, curving outward.
Yeah, a lot of friction. Next question is from Santosh. It's related to the gas separator simulator, and he's asking, is the gas bubble velocity 6 inches per second constant? How it will change for different flow pattern, and what if the gas is forming?
Those are good questions. Let me talk about the gas velocity first. In fact, let me see if I can't do this right. I'm going to escape here and go down to that
40. Slide 40.
40 right there, and then display it.
All
right. So let's talk about the gas bubble rise. Right there, the gas bubble rise is 6 inches per second on the way up. Now, on the way down, the gas velocity could be higher or different because the liquid is carrying the gas. So the only point where we see the in a separator simulator we've had the 6 inches per second sort of seen. The gas bubbles are always kind of floating inside the pump chamber at 6 inches per second, but the downward velocity is controlled by the pump displacement, and the upward velocity once the pump stops is 6 inches per second. So that's the 6 inches per second velocity. On the outside, it's based on the flow rate, and so that it's the gas flow rate, liquid flow rate. It's going to be higher on the outside of the pump. So the important part about the 6 inches per second gas bubble rise is that is in water and air. Okay, that's a 6 inches per second where that comes from. If you have inside the separator, if you have oil, then the oil is not as dense as the water, and it has a different viscosity, and you're going to have a little bit lower gas bubble rise, not 6 inches per second. Now, if you have a lot of gas and the gradient of this fluid is really light, then again the gas bubble is relative to the density of the gas, and it's even less. Now, when you say the word foam, that's what you get when you pour a beer too fast into a glass. You got all these little tiny bubbles, and you have this head of foam on your beer, and that foam is stable. The bubbles are all about the same size, but if you have gas flowing through the foam, like in the annulus of your well, if the gas rate is more than about 1 MCF per day, it will tear the little foam bubbles up and they won't exist anymore. So if you have a problem with foam, then you open your tank lid at your separator tank, you'll see a bunch of bubbles foam out of your tank because that's where the gas velocity is low. So a gassy fluid column is liquid with gas flowing through it. It's not foam. Okay? So that's the answer to the question, I think.
Great answer, Lynn. Yes, I think that clarifies a lot. Next question is related to what type of sensor was used to collect that data on those examples. So are these pump car examples from using a Polish rod transducer or horseshoe transducer? Does it make a difference? I checked some of them, and most of them are HD. But go ahead.
This data was collected with a horseshoe load cell. So up here at the very top, it shows a horseshoe load cell.
That was one of the questions. What was used, either a PRT or an HD, and the gas interference dyno card was also collected with a horseshoe load cell. But the next question here is, does it make any difference?
Not really, but the polished rod transducer, the way that the zero load line is determined is based on when the plunger velocity, when the pump is moving. So let me just go to, if we were to look at this data here for this well right here, and this were collected with a polished rod transducer, we look for where the pump fillage line is, okay, and the software is supposed to identify where the trailing valve opens, and then we look to the left, and we try to find the maximum velocity point right there after the trailing valve is open. So that's a maximum downward velocity line right there, and that becomes the zero offset. So if you use a PRT, the card sits on 0 based on that point right there, and that's probably okay for fluid pound, for gas interference, for blocked intake, because over here where the pump's not moving yeah, it works just fine. There's not a problem. The main problem is where you have mechanical friction. Then the mechanical friction becomes a zero load line, and that's not correct.
Right. Milena is asking, if I have issues with the anchor, can I identify it in a dynograph? Can I still have full pump?
If I go back to like this same slide we looked at a minute ago, this is this slide right here. Full pump, fluid level at the pump, low pump intake pressure. It's unanchored tubing. So yes, you can have a full pump with unanchored tubing. The way what you should look for is you should look for or calculate this line right here. You should calculate this line based on the tubing length and the tubing diameter, the spring constant. And if you're unanchored, then the slope of your pump card should be on the right hand side of this line because of slippage. If it's a pump card load line, when it's picking up the fluid load, is over here between the vertical line, anchored tubing, and the unanchored tubing line, then it's most likely just slippage, and you probably ought to investigate your pump clearances and your plunger size and your plunger length, because it's more likely due to slippage. And so over here we have unanchored tubing. It leans more than that, and this is the slippage. So this much loss of stroke is due to being unanchored, and this much loss of the stroke is due to slippage. So if you're thinking you're unanchored, your pump card line here needs to be to the right of the unanchored tubing KT line, or it's probably not unanchored.
Okay. David is asking, may you further clarify why FO from the fluid level is less than FO from car in a blocked intake case? That could be slide number 30.
Okay, right here. Okay. All right. So when you have a fluid level shot and you have the pump intake pressure from the fluid level shot, the pump card load is the pressure on top is the discharge pressure on top of the plunger minus 1,400 pounds intake pressure times the area of the pump. And so this is how tall the pump card should be, because you take the discharge pressure, which is 3,500 psi, minus 1,400 psi, which is the intake pressure, times the plunger size, and that's that line right there. That's as tall as a pump card can be. But since the pressure inside the pump chamber isn't 1,400 psi, it's just like the fluid level was right at the pump. There's no flow into the pump. So now when you try to pick up the load, it's this pressure on top minus 0 times the area of the plunger. So that's where the pump card load line is, because it's on the bottom of the plunger is a vacuum, 0 pressure. Did that answer the question?
I guess it does.
I think that's so. This line right here, FO from the fluid level, is calculated from the intake pressure right there, and the discharge pressure in the area of the plunger. This line, FO max line, is calculated assuming that the intake pressure is 0. So if your pump card touches the maximum line, it can only do that, kind of, if it has 0 pump intake pressure. Well, it matches the FO max line. It's obvious that the pressure is 0. Well, how can that be? Because there's no flow from the outside, the 1,400 psi pressure into the pump. All right, now that's my second chance at trying to answer that question.
I hope that's clear for David right now. No, David, you can contact us. I have one more question, which I'm not sure is totally clear. Is if I have a low pump submergency, would you recommend to increase the casing pressure to have a better pump fillage?
If your pump fillage is low, then that would be you're pumped off. That means your pump exceeds the inflow and your pump's not full. Now, if your casing pressure is like 500 psi, that means the gas pressure is pushing liquid down at the pump intake. If you lower the casing pressure, then the liquid level can come up, and you could potentially remove that back pressure on your formation and increase your pump fillage. Okay, so normally if you're pumped off and your casing pressure is too high, you can lower the casing pressure and increase pump fillage if the fluid level is at the pump. Now, if the fluid level is not at the pump and there's a gassy fluid column, and you decrease, and there's gas flowing through that gassy fluid column, and you decrease the casing pressure, then the gas flow up the casing is maintained, and the fluid level goes up, and the pump fillage doesn't increase. It stays the same, or it can even drop off. So lowering the casing pressure when you have gas interference normally doesn't help increase your pump fillage. Only if you have fluid pound conditions and the fluid levels at the pump will you increase your pump fillage by lowering the casing pressure. Okay.
Okay. Well, that's one more question from Rihan, which I asked him to review our class number 12 related to gearbox or pumping unit balancing. Is how do we balance a rod pump if it rod heavy or heavyweight? It's a totally different topic for today's class.
Yeah, I just recommend that you review that Ask Echometer session 12, and then then email us a question and we'd be glad to answer that question. So we had questions and answers just like this in session 12, Gustavo?
Yes, that's session
12.
Yeah,
So I would just recommend review that and then feel free to contact technical support at Echometer or drop any of us an email. Our emails are on the front of the presentation, and we'd be glad to answer that question offline.
That's all questions we have so far, Lynn, and if you want to go over some examples.
Okay. So if we go to TAM, in the TAM example file, there are 8 examples. And so when I go to when I click on that example folder, that TAM export file, and I click on it, then it will install on your computer in a Echometer online folder, a folder called Incomplete Pump Fillage with these 8 examples that we've talked about. And so the first example here is anchored but not set, and this one has a fluid level that's not interpreted correctly. Okay, so it looks like it's a high fluid level. The pump card's up here at FO max, and the pump card shouldn't be that tall because the FO from the fluid level line is much below FO max line. So I'm going to talk about that just for a minute. So if you go to the fluid level shot and you look at it, this is a fairly old data set, and we probably ought to change it because this data was collected with the DOS software, and this was the liquid level that was selected by the software, and the rest of the liquid level, rest of the acoustic trace, is cut off to save memory on the DOS computer, and so you can't see that there's liquid level down here. And so it looks like there's a high fluid level, but there's probably not. It's just that the liquid level that should have been selected down here, you can't see it. So that makes this somewhat of a poor example because you can't have this load line right here, FO from the fluid level, below FO max. If your fluid level's at the pump, it needs to be FO from the fluid level needs to be up here at FO max. So that's a question sometimes we get from this example well. Let's go on to the next. Like I said, I'll just go on and talk about the next one. This one is a fluid pound unanchored tubing, and if we look, the fluid level here is down at the pump. So this well has a fluid level down at the pump, and the fluid levels about 2 weeks apart. There's data on the 20th and data on the 8th, and both of them show fluid level, probably tubing anchor, and then liquid level. So the fluid level is down below the tubing anchor. There's not one drawn here, but it's down at the pump intake. If we look at the 2 data sets, the last data set is incomplete pump fillage. Again, unanchored tubing out, leans over a little more than the tubing stretch line. Probably unanchored, it was. And then here is the data before, 2 weeks before, and this data shows a full pump. So if we go to all the strokes, which only 10, all of the strokes, 1 through 10, all of them show the pump is filled with liquid. Now, if we go to the field view and we bring up the event viewer, we can overlay all these strokes and compare them if we would like. If we go click on stroke number 10 and hold down the shift key and click on stroke number 1, that highlights all the strokes, and we see that all of these 10 strokes have the same pump fillage and they're full. And then if we go close this off and look at the data that follows, there's only 9 strokes acquired. It would be nice to have gotten the first few strokes on this well when it first turned on, and then it gradually pumped off. So hopefully you see some strokes that were full and some strokes that were pulled. But it looks like we just waited. Let me show this. We just waited until we had incomplete pump fillage and we started collecting data. So you can see it's gradually changing from, let's see if we get this to work here. Let's work this way. Anyway, the main thing is that the first set of data is full, the second set of data is pumped off, and this well is fluid level down at the pump. It's a typical well that would be a good candidate for pump off controller. or a percentage timer to control runtime. And this pump fillage line is in the wrong place. It should be right here. There you go. If we go to this one, I'm going to skip this gas interference one. I'll come back to it in a minute. The next one is a hard pound. The pump stops. So if I go to look at this well, this is a well that there's a paper called Percentage Timer. And this is a well that the Percentage Timer paper was based on, and it's a pretty. Let's see if we got a fluid level shot here. There's not even a fluid level shot. The fluid level down to pump. So if we look at this well, it has a pretty sudden drop in the load as the plunger gets close to the bottom of the stroke, and so this is low liquid fillage, quite a bit of gas in the pump, but it's low pressure. Now, notice that if the tubing were unanchored, the line would follow, the pump card would need to be to the right of that line. And so this well, the tubing is anchored, but this is slippage from here to here. Okay, so see that little distance? It's got anchored tubing, but it's I would say it's not unanchored. Now, if I go look at the analysis plots on this well, and I plot the pump card here on the bottom, and I plot the polish rod velocity here on the top, and the plunger velocity on the top plot, then this is in elapsed time in seconds, and this is in plunger position here on the bottom. So if I look at the plunger at first, when it picks up the fluid load, from here to here, it picks up the fluid load, and notice the plunger velocity is 0. See right here, it's from 0 time to about that time right there. The plunger velocity, the first second, is close to 0, and then right here, the plunger takes off, starts to move as the trailing valve, the sustaining valve starts to open, and it quickly speeds up, and at that point right there, the plunger velocity is moving up faster than the polish rod velocity. And you can see here it kind of dampens. Those are echoes. Echo. It's kind of dampens out right there. And so there's our so here we're moving along at peak velocity, and we're on the upstroke, and we're going fairly fast as or faster than the polish rod, and we get to the very top of the stroke. The very top of the stroke's right there, and the velocity of the plunger is going to become 0. See right there, 0 velocity right there at the top of the stroke. Now this vertical line may be some stuffing box friction. It's not very much, but it could be stuffing box friction. Okay, so there you see that flat line right there, and then we start compressing the gas. This is low pressure gas, so we start compressing the gas, and the plunger velocity is the same velocity of the polish rod. See how that's just the plunger velocity and the polish rod velocity. The polish rod velocity is like a best fit curve fit of the plunger velocity. So here you can say that the plunger and the polish rod velocity are the same, and they're both going down really, really fast. And then right about there, the plunger starts to slow down. Why? Because we're starting to have the gas pressure inside the pump go up. So we're starting to compress the gas inside the pump chamber, and the gas pressure is going up, and the plunger is quickly slowing down, and the plunger almost stops right there. See, there's 0 velocity. So right about there, the plunger's almost stopped right there, and the polish rod's going down pretty dadgum fast still. And so at that point, if you looked at the polish rod, and you're about, 20 inches off the bottom of the stroke, you see the bridle wiggle, and you say, go feel of it, and you say, man, feel that plunger pound into the liquid. But that's not what's happening. What's happening is the plunger is slowing down, and that's causing the bridle to twist, and the plunger's not actually right here pounding the fluid. It's just slowing down to compress the gas. And then as the gas compression opens the trailing valve, then the plunger is starting to speed back up, and then it's going down and downstroke, and the fluid inside the pump chamber is getting displaced in the tubing on the downstroke. So this graph is a typical normal graph analysis plot that you can make when you have fluid pound conditions, and you can study the idea of when the valve opens right there. See, there the valve starts to open, and the plunger starts to speed back up. Now, if we go look at the blocked intake, remember this is the plunger slowed down before it came in contact, before the trailing valve opened. It slowed down to almost zero velocity. If we go pick the blocked intake card, this one right here, choked intake, blocked intake card, and we look at the same information on the velocity plot, the polytrod, and the pump, and I'm going to turn this into, this will be fine. We'll leave this bottom one, which is a plot of pump load versus plunger velocity. And now I'm going to take this and I'm going to move to the right. See right there, it's got fairly low plunger velocity as it's stretching the rods to pick up and then right there the trailing valve opens. Trailing valve opens, plunger takes off, starts going really fast, and there's a harmonic right there. And now it's on the downstroke, and the plunger and the polish rod are going the same speed. Actually, the plunger right there is going faster than the polish rod. And then it's still going fast, and then bam, it hits the liquid, and it didn't slow down at all. And then it stops after the trailing valve opens. So it stopped after the trailing valve opens, where before the plunger almost stops before the trailing valve opens. So blocked intake, you often see this pause after the trailing valve opens, whereas on a low pressure gas interference or fluid pound card, you'll see the plunger slow down over here before the trailing valve opens. So when you look at this data, it's sort of weird because during this time it stopped, there's no negative load. The negative load is right here after the plunger starts to move again. And that's where you see that impact load. So if we turn this, let me turn the plunger velocity off. Turn the plunger velocity off. Now I'm just plotting pump load. I'm going to pull the pump load line over to that negative load right there. And I plot this versus plunger position. That negative load is after the plunger has stopped for a while, after it pounded into the fluid and stopped. And then you see that negative load. And this, I can't say always, but I'm going to say almost always. On a blocked intake, you almost always see this negative load. Whereas on a fluid pound card, you hardly ever see this. You never see a negative load. So in the past, Jim Lee and I have argued a lot about why you call a fluid pound card a pound, because it's not really pounding the fluid, because you don't see this negative load. And so when we were arguing about it, I said, well, I'm going to find some pump cards that show negative load. And the only pump cards I could find that show negative load were blocked intake cards. And so that mechanism of opening the trailing valve is different when the intake is blocked than when you have a well pumped off, and you almost always see this negative load, this pound, when the intake is blocked. Okay, that's probably too much, but that was. Now the gas interference card is one we've had in a lot of the examples so far, and the gas interference card is a mark unit. So I'm plotting it from, I process the data from top of stroke to top of stroke, and so this is top of stroke to top of stroke, I think. And it looks kind of weird. It's not the same kind of plot as the other ones. And so what am I saying when I say top of stroke to top of stroke? If I go click on raw data, and I look at the load versus acceleration data, there's a button called reprocess. And so when I click on reprocess, then there's an option, well, it says histogram, but you can click top to top. And so I thought that we'd process that data from top to top, but it doesn't look like we had. But you can click, let's just say TAM real time and reprocess and say yes. And if we go look at that data on the analysis plot, it still looks the same. I'm not sure why. Okay, but anyway, you can process different types of data, load and position data, acceleration data differently. The reprocess button is important sometimes when you have a tag at the bottom of the stroke. If you reprocess it top to top, the tag will go away if it's not a real tag. So sometimes I use the reprocess top to top option to see if there's a tag at the bottom of the stroke, and that's how I often will use that. If I go to the details tab on this well, and I pull this line over to right about there, then the software puts this line here called the gas free pump fillage line. So from this line to the top of the stroke is how much gas entered the pump chamber at the intake pressure. And from this blue line to that line is how much free gas is inside the pump at the discharge pressure. And so to see more about that, so if you want to know more about this gas interference idea, you click on the pump card analysis button and you go over to the pump displacement tab, and it says that in this well we lost 114 inches of pump displacement due to gas interference out of about 155 inches. So there's only 35 inches of used pump displacement from here to here. That says 40, but we also lost some slippage, which is about 10 inches. So this table shows us that the free gas in the pump went from 114 inches down to 19 inches. So it went from 114 inches right here down to 19 inches right there, compressed to a discharge pressure of, let's see, I think the discharge pressure right there should be about 692 intake to discharge. That is about 1,800 pounds of discharge pressure. So that's what we require to open the trailing valve. So we go from 700 pounds of intake pressure, we move the plunger down, and the pressure is going up inside the pump chamber until we get it right about there. And right about there, the pressure inside the pump chamber, I can't move my mouse over there, but right about there, the chamber pressure exceeds the discharge pressure, and the trailing valve pops open. That's what the little animation shows on the left-hand side. If I move my mouse over there, it'll go to the bottom of the stroke. So if I sneak over, yeah, right here. So I snuck my mouse over there. But the idea of opening the trailing valve, it opens based on this point right here. When that point right there, the pump card load causes the intake pressure to exceed the discharge pressure, then the trailing valve pops open with pressure. Okay, that's maybe you got one time for one more. I'll pick on one more and then we'll go on. The Sandia data has this is probably if I had to pick a favorite pump card in the whole wide world, this would be it. It's hard to imagine that's my favorite pump card. But anyway, this is my favorite pump card because this is the data that was measured at the surface when a downhole load cell was ran in the well at the pump. And this data here that we calculate based on the surface loads matched what was measured at the bottom of the well. And so this is the Sandia downhole pump card, anchored tubing, high gassy fluid levels, almost flowing, and a little bit of gas interference. So very similar in shape to the pump card that I show right here. So this is the same time and the same pump card right here. You know, it's scorched in. I could probably go back to the TAM data and take this here and you know, scorch it in. It's going to look more and more like the same data. All right, so that's the end of my presentation. I hope you all enjoy this presentation. I'm glad I enjoyed presenting with Carrie Ann. I thought she did a great job. So that's about it. Carrie Ann, it's your turn to talk.
All right. Well, thank you, Lynn and Gustavo, for handling the Q&A for us. We would like to thank all of you for joining us today, for the great questions and feedback. We hope you enjoyed it and learned something new. And in the event you have any follow-up questions, we always welcome your calls and emails. So next week's session, we'll be concentrating on navigating the dynamometer features inside the TAM software, including the dynamometer analysis tools that are available to you. If you're on the registration list for the weekly sessions, you'll automatically receive a link to next week's session. Otherwise, please go to our Ask Echometer webpage, and you can click the link to register for the Ask Echometer sessions, and then I'll send you an email with the link for next week. So we appreciate your time today, and we're so glad you joined us, and we look forward to seeing you all again next Wednesday. Hope you all have a great week. Thank you.
Thanks.
Thank you all.